Perfect. Thanks very much. Hi, everybody. My name is Denny Lee. I'm a developer advocate here at Databricks. We are having a fun session called Getting Data Ready for Data Science with Delta Lake. The session will be slides, of course, but we'll definitely do demos. And on top of that, we'll also go ahead and have a live Q&A. So if you have Q&A, please go ahead and click on the panel for Q&A and actually add your questions there, just because that's the best way for us to see what's going on. Okay. So, and my apologies for those who are not currently in the Pacific time zone, then good evening for you folks as well. So, or good afternoon for that matter. So, who am I? Let's start off with that. Well, as I said, I'm a developer advocate here at Databricks. I'm a hands-on distributed engineer and systems engineer with data science background. I basically helped build internet scale infrastructure. I was at Microsoft, part of Bing, and also part of SQL Server. I was on the team that helped build what is now known as Azure HT Insight on the Project Isotope, and worked with very large implementations of SQL Server and Azure implementations. And been working with Apache Spark since 0.5. So at least I can have a good sense of imposter syndrome to be able to talk a little bit about Spark and data engineering. So before I go into into the session, a little about Databricks. We are the company that accelerates innovation by unifying data science, engineering, and business all together with our unified data analytics platform. So the company, or the founders of our company were the original creators of Apache Spark. We've also created Delta Lake, which is part of the Linux Foundation, MLflow, and as well Qualys. These are all really cool open source projects that I'd love to go talk to you more about. I'm going to focus today primarily on Delta Lake. So just to give some context about the Apache Spark, if you're unfamiliar with it, the Apache Spark itself basically is, at this point, the de facto unified analytics engine. It's an important aspect actually to call out because it's one of the few frameworks that's able to uniquely combine data and AI, where on the left-hand side, as you're seeing here, we've got big data processing with ETL, SQL, and streaming. On the right side, we talk about machine learning, MLlib, and Spark R. Well, these are things that Apache Spark incorporates, and it can ping a lot of different data sources, whether you're talking about S3, Azure, Hadoop, Kafka, Parquet, and other ecosystem source ecosystems. And so that's part of the reason why you see Apache Spark as the de facto unified analytics engine. Apologies for that. So let's talk about what the theme of today's session is, which is to get data ready for data science. Okay. We're not going to go cover all of the different aspects here just because it's a lot, to put it rather lightly, right? But basically what you have here is the data science lifecycle. It typically starts with data preparation, and there's a whole set of tools that are involved with that, okay? You've got, of course, Spark, but then you also in the ecosystem, you've got SQL native, not just Spark SQL, various aspects of Python, scikit-learn, pandas, where you're going to prep the data, okay? And then you're going to need to figure out how to tune, scale that mechanism of data preparation. There's a lot of ETL that actually has to go into this in order to get to a point where you're actually able to train the data. Then when I flip to the training cycle side of things, there's a whole set of other tools, which is like sklearn, PyTorch, also Apache Spark, R, XGBoost, TensorFlow, and so forth and so forth. And if you happen to be using a technology that I didn't mention, it was not so much it's not meant as a call out against your technology, quite the opposite. It's just that the ecosystem for training and all these other technologies is quite large. And you're going to have to tune and you're going to have to scale that, because after all, when you're training, there's also a whole set of hyperparameters that you're going to have to go ahead and deal with, right? And you're going to have to tweak them, change them, optimize them, right? So this is the reason why it's so important that you actually have a mechanism like MLflow, which we'll show you at the tail end of this session, to track all of these different variables. And then, all right, now you've trained the model. Now it's a model exchange. You're going to have to deploy it. And again, you can do it with Apache Spark, or you can do Docker, Azure Machine Learning, SageMaker, and there are all sorts of mechanisms for you to deploy this, basically, which may or may not be the same set of technologies that you do. And that goes right back to the raw data, because after all, once you deploy it, there's going to be raw data that goes into it. You're going to have governance to ensure that the data itself actually it will follow GDPR or CCPA compliance rules. We're going to go into that a little bit during today's session, because an important aspect of that getting data ready for data science is exactly that: the ability to ensure you have GRC, as in governance, risk, compliance, covered, so that way you can ensure that any aspects of security, but more importantly, not importantly, but more and just as important, aspects of privacy are covered. And then in order to scale that raw data, again, you're going to be using things like cloud storage or Delta or Kafka or Hadoop or whatever else. And then as more data comes in, it's going to change, right? It's not just like BI, where it's just about aggregates and I happen to report a trend, right? Those trends or those changes because there's more red dongles purchased, or more warmer temperatures, or whatever else, invariably not just affect the BI reports that you will report out, but just as important, if not more important in this particular case, the data science you're going to do against it, the machine learning models that you're training against. There's basically this concept of model drift, right? And it begins with data drift, right? The changes in data over time. And this is normal, right? It's an expected aspect of how things work. And so this is a continuous cycle, right? It's not like it ends at one point. If you're successful and you're able to build excellent, awesome machine learning models, deep learning models, or whatever it may be, you're going to continue doing this, right? You're going to continue training. You're going to continue deploying, continue getting new data. So in other words, not just the data that you have, but adding new additional data sources that maybe you originally never processed. Then you join that data. And then you have to prep it again, and then you have to train again and deploy, and so forth. So it's a vicious cycle. And an important aspect of that also is that now that I just covered some of the technologies that are very common in that data science lifecycle, if I was to ask for a raise of hands, obviously we're on a YouTube Live / Zoom setup, so it's going to be a little bit difficult for us to pull that off. But if I was asking you to raise your hand, how many of you know all of the technologies that I've listed here, and for that matter, all the technologies that actually are used in your environment? Okay, so forget about even my list. Just talk about your environment of every single technology. Are you an expert with Kubernetes to all the way to PyTorch, right? Are you an expert of every single one of those technologies, right? And while I'm sure there's some heroes that are listening to this session here today, the reality is the vast majority of you not only don't know all these technologies, really don't have the time to learn every single technology, because you're actually trying to be great at one of these technologies, right? And so that's a focal point for us, which is how do we survive this data science lifecycle? Well, the first things we often need to do when we, the first thing we often need to do when it comes to the data lifecycle is to focus on this concept of the role of data engineering, okay? Data engineering actually ultimately becomes a very crucial aspect of how you actually deliver data science. And even today, there's far too many teams that are actually built up incorrectly. So what ends up happening is that data science is the tool du jour, or the word du jour, or the job career du jour, and it deservingly so. So don't get me wrong, I'm not trying to insult anybody who's a data scientist here. Quite the opposite. I think it's an awesome job. The context I'm coming from is more of the fact that we hire all these data scientists, but we don't hire any data engineers, okay? And so this actually becomes really problematic, right? Because what ends up happening is that the data scientists themselves, she will actually have to do the data engineering, right? It's not about the fact that they actually have to, because it's not like the data will magically appear in tabular format, cleansed, partitioned, in Parquet, with no data problems whatsoever. I mean, if you do, that's great, and I'm really happy for you. But in reality, that's not what happens, right? What actually happens is that you've got a lot of data. You have to filter it out. It's dirty. You have to aggregate it or augment that data. All right. So in that process, right, you actually need data engineers to actually bring software engineering rigor to that process. And it's not meant as a, okay, now I'm going to make a data scientist into a software engineer. Again, if you want to, that's awesome. And in fact, we can probably have another discussion about rigor, software principle rigor within data science itself. But before we can even talk about that, we actually need to talk about the rigor for data engineering. And so, for example, in one of my past lives, I was at Concur, now purchased by SAP. I had helped build up the data science engineering team. What ended up happening there was that we had, the company had hired a lot of data scientists first. And so really smart people, but they're all using a disparate set of tools, right? And some were standard, some were not. And because they were using disparate set of tools and they were really working in isolation from each other, what resulted is that we had different copies of the same data all over the place. This resulted in a problem where the data itself wasn't clean, right? Or it wasn't following the same business rules, right? And so one of the first things I had done was to bring in data engineers, or data science engineering, specifically engineers that were focusing on the aspect of how to get data cleansed and organized for data science. All right, and then exactly as we called out on the slides, it allows us to develop, test, and most importantly, maintain those data pipelines, right? So you have these very reliable, quality data for quickly, efficiently, and securely, right? That's what you need. You need reliable data lakes. We're going to talk about data lakes shortly, but this concept is that whatever data source that your data scientists are going to work with, it actually needs to be reliable. And this ends up becoming a paramount importance in order for you to have successful data science projects. So when you look at these like big data architectures, right, it starts typically, and I've oversimplified it just because that way I don't have to give you a gigantic burger style of all the different batch sources or all the different streaming sources. You've got input sources. Typically, it's actually really broken down by latency. Either it's a batch or it's streaming. Batch could be all sorts of things: a file source, cloud source, database. Streaming could be your your streaming, pinging of some form of REST API, whatever else, Kafka Kinesis, Azure Event Hubs, things of that nature. All right. Ultimately, you're going to want to put this stuff in a data lake. Okay. This concept of a centralized single source of truth, but it's excuse me, not really a single source of truth from the standpoint that, oh, it's completely utter trustworthy, at least not yet. Right now, up to this point, it's actually a store, right? Basically, I just dump any and all data that we have. And this, when we brought in the Hadoop stage of the data lifecycle career, right? That was it. The great thing about Hadoop was that we could just take all the data, store it into our file system. It automatically would replicate it, so I could make sure it's reliable, where I wouldn't lose the data. I had to deal with concepts of eventual consistency, but nevertheless, the data was there. Yay, I'm good to go. Problems that, and then we would do merge schema on read, where basically at the point in time I was querying the data, I would actually get the schema out of it. But guess what? Like, that's a lot of data. And we weren't sure what we were keeping. Maybe we need to filter that out. Maybe we need to cleanse it. Maybe we need to go ahead and actually remove it because it's actually corrupt. But nevertheless, now we have a data lake. And so, and there's ultimately a data consumer. Now we talk about AI, we're talking about machine learning, deep learning, BI. And from where I'm sitting from, at least from a standpoint of reliable data lakes, there's actually no difference, right? It is very much about this concept that you're going to have consumers that look at this data, that want to understand how this data works, okay? And that's it, right? So whether they're running a machine learning model or they're running a BI report, they're the data consumer. Basically, that's it. All right, so these are the basic concepts. with these input sources or your data lake, you've got a store for structured and semi-structured data. Excuse me, please, sorry. You pull data in from various input sources. There's a single central location to access all this data, basically breaking this data silos. That's what's great about this, that everybody can come in, whether you were all the different teams, instead of actually working separately from each other, we can just all go to this data lake and grab that data. That's awesome. All right, it's open accessible format. There's no vendor lock-in, and SQL machine learning against that single source of truth. So big data architecture like this, where you have a data lake, that's super promising, super awesome, but there are always issues with that, of course. And these are the data reliability challenges with the data lakes, okay? If you have failed production jobs, it leaves data in a corrupt state requiring tedious recovery. What that means is, like, for example, you're running a Spark job or a Hadoop job or whatever, right? It's multiple tasks. The task fails, the entire job fails. Well, it's written something to disk, right? And if it's written something to disk, that means at that point in time, when somebody else goes ahead and reads from disk, and disk in this case could be cloud storage, so I'm not trying to specify one or the other, there's a bunch of remnant data that actually could be read that's actually not trustworthy. It's not reliable. It's not something you want to actually be reading. All right, so that's actually a big problem, especially when the more data you're working with, the more likely jobs will fail. And if the jobs will fail, that means your data scientists are writing algorithms that actually are reading data that's actually incorrect, which is really, really bad. Excuse me. Okay, so there's a lack of quality enforcement, which means there's inconsistent and unusable data. That quality enforcement could be something as simple as your schema. In other words, there's an additional column that's noted inside the source data, except the source data had an extra comma, not because mainly because there was a corruption, or because it was actually a text with comma in it, but because of the comma, and it was a comma into the file, the code base never understood it, so also it's actually adding an additional column to the data, thereby putting incorrect data in the wrong format. So when you read it, you're actually reading the wrong thing. All right, and the final thing, but the most important thing, is lack of transactions. This lack of transactions itself basically prevents you from ensuring that trustworthy data set, that corrupted data. When you, for example, have a failed production job, right? If you actually had a transaction protecting it, what would happen is that the job fails, anything that you even wrote to disk, it'd actually be reversed. It would remove the files that were written, okay? Because that's actually what a transaction would do, right? This is what traditional RDMSs, relational database systems, are actually able to do. And this lack of transactions makes it nearly impossible to actually combine batch and streaming together, right? Because as you have streams of data running in at the same time, when at what point can you trust the data as it's coming in? Well, if you have a transaction that'll protect it, then sure, then you've got something to work with. But if you don't have a transaction protecting that data, you don't know if the data that's being written in here actually is the final state. And so how can you then combine that with your batch data? All right. So now let me look at the pipelines, okay? And so with those pipelines, this actually gets really funky really fast, right? So for example, I'm gonna just happen to use this particular design. You can use something else, whether it's Kinesis or Azure Event Hubs versus Kafka, but I'm just gonna use Kafka for example. So when you have these complex pipelines, you're increasing the engineering overhead. So the events go into Kafka because you're doing streaming. So you're gonna you'll run Apache Spark structured streaming against Kafka. It'll get written to the table. The table gets continuously written, and then, for example, there'll be a stream that goes from the table for your reporting, right? But these Spark jobs get exponentially slower as there are more and more of these small files, because that's what happens with streaming jobs, right? You create lots of really small files. The more files there are, the more overhead there is for Spark, or for that matter, any system, to go ahead and read those files, and that overhead basically slows down performance. All right, then let's add the fact that, okay, well, how about if there's late arriving data, right? In other words, the data that was supposed to be processed every 5 minutes or every 10 minutes. In fact, there's data from 2 days ago that they forgot to process. I need to go back in and process it. So that means, in that case, I have to potentially delay processing because of the fact that there's the delay in that data. And then, okay, maybe I can change that where I have the continuous stream, but then what I do is that I have the left table that where it's receiving data that's constantly streamed in, but then I have a batch process that goes ahead and compacts it and organizes it so that way it takes care of the late processing delays. Okay, so now it's getting increasingly more difficult. Okay, but then more of the times than not, this latency doesn't satisfy business needs, not to mention it's getting more complicated, right? So then what do you typically do? You typically switch to, oh, well, then let me do a Lambda architecture. This Lambda architecture where I have streaming and I have batch. So the upper portion is where I'm streaming, and then I have this Kafka to the stream to unified view of the streaming and batch data. So your AI reporting can go off that. Meanwhile, I have batching data that where I have another streaming against Kafka at the exact same time that writes the data to the table on the bottom left. I have a batch process that goes ahead and processes the data into the table. It processes it in batch, so that way we can take into account of the delays in data, and the batch processes it into the unified view. Now the unified view has both streaming and batch. Okay. And by the way, I'm going this fast not because I'm trying to emphasize that you're supposed to listen this fast. I'm going this fast because I'm trying to explain to you this gets more and more complicated as I go through every slide. Okay, so now the problem with that particular option is that you're going to actually have to have a validation check that checks the data that goes through the upper streaming to the top left streaming, so that way we can make sure the batch data and the streaming data are actually have the same values. Otherwise, your unified view will actually result in reconciliation problems. Okay, and then if you need to fix mistakes, well, the validation takes care of the streaming data, but you need to go ahead and reprocess the data that gets written to the batch on the bottom left, and so forth and so forth. Okay, so this becomes really, really complicated. And then, oh, not to mention updates and merges. Right, again, this is really complex thing to do. Okay, now I'll stop and breathe. The question then is, can this be simplified? Because in the end, I know many people who are saying, hey, I'm a data scientist. I want to go ahead and talk about algorithms, but this is the reason why we did talk about getting data ready for data science with Delta Lake and MLflow, because we're trying to get across the point that there's all these data engineering pipeline steps that you have to do before you get to do the fun stuff. We'll actually have sessions later on which dive into all the different machine learning algorithms that are available in Spark ML. And so definitely chime in some comments so we can know how to customize these tech talks, so we can talk about stuff that you guys are interested in, but or which algorithms you like us to tackle first, like XGBoost or PyTorch or whatever else. But the point is that before I can even go to that area, I need to make sure I can handle the data in production, right? Because in production, this is the scenario we have. And of course, the question I'm going to ask is, can this be simplified? Even if I had a dedicated data science engineering team that was focusing on building these pipelines, this is a lot to maintain, right? So how can I simplify this? And so the key thing to simplify this is that we want to introduce ACID transactions back into the fold. Okay, and so ACID basically transactions were popularized because of relational databases. Okay, what they did is that they introduced this concept of atomicity, consistency, isolation, and durability. We have actually separate videos that go into the details of what those mean, but the context basically is that if you write something to disk, cloud or on-prem, it means it's got written. If there's an error, it will fail out. Any other clients that are concurrently trying to read from it can reliably know that the data is either there and for them to read it, or it isn't, and we'll get that information right from the get-go. If you're concurrent writes to the system, we can actually, those with ACID transactions have the ability to coordinate the fact that there are concurrent transactions and prevent corruptions, overwrites, and any other issues. Once you have that, you can actually handle batch streaming updates, deletes easily. For example, if I go back to my days at SQL Server, right, I could handle streaming and I could handle batch at the same time in my one single database, because I had ACID transactions where it allowed me to do super fast OLTP, where I was like, financial services was writing data to the disk super fast, and it was no problem. I could handle it because I had ACID transactions. At the same time, I was going ahead and doing batch processing of aggregate data or of other sources data that I'll eventually join with the financial data. So again, I could go do that. The problem, of course, is that I couldn't scale it, at least not to big data internet scales type sizes, right? If I could get a database to do that, I'd still be at SQL Server. And this is not a knock at SQL Server. It's a great product. It's just simply saying that when I have to work on big data problems where I have to handle streaming and I have to handle batch and machine learning, data science, all these other things all together, this is why we started looking at things like Apache Spark, right? And then in order for a data scientist, for you to even do BI reporting reliably, we needed to reintroduce ACID transactions back into big data systems. And that's actually why Delta Lake's there. Delta Lake is allows us to bring ACID transactions back to Apache Spark and big data workloads. So ultimately, you get consistent reads and you get rollbacks. So in other words, if there's an error, I can roll back on that, which is pretty sweet. So Delta Lake, as we say here, right, it is a open format based on Parquet with transactions utilizing the Apache Spark APIs, okay? It allows us to address the data practitioner's dreams, process data continuously and incrementally as new data arrives in an efficient way without choosing between batch or streaming, right? It's the same difference to us, right? So that previous screen that you had, you simplified it. So it just becomes this one line for sake of argument that you're looking at, which is sort of nice. All right. The key features of Delta Lake is that it has ACID transactions, schema enforcement, unified batch and streaming, and time travel with data snapshots. And we're actually going to demo that in a few minutes from now. Okay. So that way you can get to see it and showcase it. Okay. Included with this concept is a concept that we call Delta architecture. So in other words, when you design your systems, what you want to make sure that there actually is a continuous flow model that allows you to go ahead and unify the batch streaming. So how you do that is that you start with your source and you build, in essence, what we deem as a bronze table, right? This is raw ingestion. This is similar to how you traditionally use your original data lake, okay? You dump the data in there and you're basically good to go, right? That's how you basically start off, right? It'd be equivalent to basically saying, I'm doing lots of inserts to the data. So what ends up happening here is that you have that, okay? Then you have silver, right? The silver basically is filtered, cleaned, augmented data, okay? And then, so what that means is that when you process the data, when you process the data, you can filter out, for sake of argument, all the logins that you don't need or whatever else that you want to do, okay? You can clean the data and augment it with additional information from other sources, and you can combine that together, okay? And then there's gold data, okay? So this is where you can then run your business level aggregates. This is where you can do your AI, your streaming, your AI, your data science, your machine learning, deep learning, things like that. This is where then often you will do your merges and your overwrites, okay? This isn't to say you can't do inserts in gold or you can't do deletes in bronze. It's just a simple saying that from a particular traditional data flow perspective, basically, our data pipeline perspective, it is more or less like this. You inserts in bronze, deletes in silver, merges and overwrites in gold. All right. And like I said, it ultimately goes ahead and allows you to do your streaming analytics and AI reporting. It also allows you then to reprocess the data as if there's corruptions, issues, or with the data, or changes in business requirements that require to reprocess because you have the original raw ingestion. You can go back to the beginning and reprocess it, so you have the silver and gold data again. So this is the concept of a Delta Lake architecture. Okay, and basically each step that you see here is a progression of how you can make things cleaner. Okay, how you can the data quality basically goes up. All right. This architecture then reduces the end-to-end pipeline SLA, reduces pipeline maintenance burden, and eliminates the Lambda architecture for minute latency use cases, okay? And so we make this architecture real because you've got the open optimized file source, ACID transactions, scalable metadata handling for high throughput, insert updates and deletes, okay, data versioning, and schema on write option to enforce data quality. Now, I skimmed through this really quickly because I'm going to show you how that all this works. So, so you know what? I'm actually going to stop presenting now, and I'm actually going to go right to the demo because I'll end with the how do I use Delta Lake. Okay, so give me a second. All right, perfect. So here's a notebook, by the way. And by the way, this notebook will be available for you to go ahead and download and use yourself. Okay, so this is you can use it on Databricks Community Edition. So you don't need to purchase Databricks to do this. It is a Databricks notebook, but you can use on the free DBC. I even call that out actually here. Okay, now what I've done up to this point is I've just created a quick table that looks like this: address. Sorry, the state and the counts. Okay, basically what we're doing is we're counting the number of loans. Okay, that's all we're doing. Okay, so let's think here. Now, in order for us to do this, what I first did is I easily converted this from Parquet to Delta Lake format. So what I did is I basically, in this particular case, simply ran a create table by statement. So I basically converted what used to be Parquet into Delta Lake. There's actually a Delta Lake one-step migration API as well that allows you to do that, but I just happen to do it this way. Nevertheless, now I have a Delta table. And this Delta table, basically, you'll notice it says here's Delta, DBFS, this is the Databricks file system, loan by state Delta. I've called out the partition columns, things of that nature, and you're good to go. Okay, so in other words, it's basically let you know the schema. All right. So I've just done this real quick setup. Now, what I will do is I will now run it live from this point onwards. Okay. So if I look at the file system, what you'll notice basically as it's showing its stuff, okay, is these are all the different Parquet files. And so this looks pretty similar to just pretty much like any other Parquet set of data that you actually are used to, okay? You have a table, loan by state Delta. It has a bunch of Parquet files, yay. Except the one big difference is this Delta log folder, okay? And the Delta log basically is exactly what it sort of implies. It's a transaction log. Every single transaction, every single change, modification to the data is recorded, and it's recorded in this format. You'll see this basically these JSON files. Okay, and so the _delta _log contains those JSON files. So you only see one of them, the 0 file, mainly because that's the creation of the table. All right. So let's go ahead and actually run a streaming scenario where I'm going to go ahead and do a unified batch and streaming source and sync. So what you notice here is that I have this Delta Lake Silver path that I initially had set up. All right, I'm going to do a read stream, i.e. I'm going to run a streaming job, and I'm going to read whatever data is coming out from that Delta Lake Silver path. That's this path here, by the way, that I had called out before. All right. So now I'm going to go read that stream. In this case, I'm just going to output the data by state. So my apologies for you non-Americans. The data set I have is currently only for the United States. Okay, so the explanation of this particular data set, by the way, is that these are loans. Okay, so these are loans by state read stream. Okay, so in other words, the number of loans for each state that we have. Okay, so let's let that sucker run. So perfect. Okay, I'm going to answer some questions real quick as we run this through. If for some reason it's running a little slower than I expected, actually, you know what? I'm going to see if I can just run it from here. Oh, that's why it's always good to have a couple backups. Aha. All right, so I'm just going to skip that step. I'll let this step, and let's run. Okay, cool. All right, so this one's running a little faster today, so I might use that one. Okay. So as I wait for the initial streaming jobs to kick in, basically, the quick call out is this: will this recording of the Zoom webinar be available as well? Yes. This, just as a quick note, this webinar, this tech talk is going to be available for you to go ahead and work with. No problem at all. Okay. So all right. So for some reason this one's running a little slow today, so I'm just going to use this one. Haha. All right. Cool. So right now, poor Iowa is null. Okay, there's no values for Iowa. So let's just go ahead and run that right now. This is the great thing about live demos. So I'm just going to insert data into it. Now, note the fact that I'm inserting data into loan by state Delta. What that means is I'm inserting data into the batch table, not the read stream, not the write stream, but the batch table. It's ultimately going to the same file system, but it's right now doing a batch process of insert as opposed to doing a write stream. And what you notice is that Iowa is slowly, steadily building up more data. As you can see, that it's progressing from 450 to 900 because I'm just doing an old school insert here right now. But the context, and by the way, in production, you don't want to really do it this way. I'm just doing it so that way you can see I'm doing a batch write to a read stream concurrently. That's actually all I'm trying to do here. Okay, so that's just a quick call out here. Okay, so all right, so I believe most of the data has been processed already, the 6 loops. There you go. And for that matter, I will go ahead and take a look at the data here. So if I go ahead and look at the log, oh, sorry, I forgot to stop. There we go. You'll notice that now I have multiple files. That we have the original 0, but we have 1, 2, 3, right up to 6, all here. These are the 6 inserts associated with what you of the 6 insert statements that you have here. Okay, and we'll show you actually how that looks in shortly. I just want to show you the file system first, and then I can go back to the loan by state delta. Right. So in other words, I had the read stream, which was showing it all here. Okay, but I can also go ahead and see it back in the batch, and sure enough, this is the same value. It doesn't seem that interesting, but the important aspect here is that now I can read and write, whether it's streaming or batch, to the exact same file system, and I can do so in a reliable fashion, and that in itself is a very powerful thing that I can do. Okay, and so what's also great about Delta Lake is that now if you are thinking yourself like I am somebody who is used to using SQL syntax because for sake of argument, you come from a SQL background, or for that matter, you just like the syntax, which is understandable. What's great is that you can now run with Delta Lake with Spark. You can actually run deletes, you can run updates and merges. Okay, so for example, I just created the same version of the same table, except I'm creating a PQ one, i.e. a Parquet version of that. So for sake of argument, if I was to run a delete, okay, it'll fail, right? The delete only works when it's supported by Delta. So not a big deal. It's because I realized, wait, no, I wasn't supposed to put that data into Iowa. I was supposed to put that data into Washington. So no problem. I can go ahead and run the delete right there. Okay. And so boom, now that delete's done, I can just go run this particular statement and I can look at my state all over again. And I'm back pretty much to the 0th where Iowa is null. Okay. So now I want to run an update statement. So this is like our 7th command is basically doing the update. The delete. The 8th command is doing this update where I'm going to try to update it because it was those 2,700 value that I saw there. I was actually supposed to give it to Washington, not to Iowa. Okay, so of course it fails with Parquet. So again, these failures are actually designed to happen. So by the way, when you get the notebook and you upload it and run it, you'll see 3 errors right away. That's where the 2 of the 3 errors that you just saw. Okay, you'll see the 3rd error pretty soon. And so then we have the update statement again, same idea with Delta Lake. I can go ahead and do that right away. Not a big deal. We're good to go again. Okay, and then again, let's review the data. Sure enough, here you go. Okay. So Washington State has 2,700. Okay, and then same idea. If I want to do a merge statement, so the reason I'm just going to run that. Obviously, I'm just going to run that in Delta at this point because I think I've nailed that point across. I want to update Iowa to 10. I want to change California to 2,500. I want to make Oregon null for some reason. So nothing against Oregon. I'm actually born there, so nothing against them. But normally a merge statement is actually these 7 steps: identify new rows that to be inserted, the same row, new rows that have to be replaced or updated, rows that are not impacted by an insert update, create a new temp table for where all 3 inserts have to occur, delete the original table, rename the temp table back to original table, and drop the temp table. Okay, that's what a merge is usually. Okay, if you were to run this yourself in a standard distributed file system, or you can just run this one merge statement. In Delta Lake. So again, we try to make things a little bit simpler. So again, we made California 2,500, we nullified Oregon, and sure enough, Oregon's null, California's 2,500, Iowa's 10. Okay, so this is really cool stuff. All right, but I also want to evolve the schema. So for example, the counts that I have here right now, that's just simply the counts, right? That's all this is. It simply tells me the count of loans. Over time, the real business value of should be actually the dollar amount. So I've generated this, by the way. Okay, this is obviously fake data. Okay, so I've got the state, I've got the count, but now I've got the amount. And so now I want to just go ahead and say, yeah, let me include that amount information because that's super important. Well, that's the fourth error here, because we actually want to enforce the schema. So this is actually a desired error. In other words, as you're putting data into your data lake, with Delta Lake, you basically ensure that you're not going to overwrite the data that you have there, or you're not going to go ahead and put potentially corrupt data, because maybe it was human error. We weren't supposed to put the sum amount data inside there. It was by accident. Okay. Well, that's fine. So with schema enforcement, we're actually preventing that from happening. But if I was able to add this option merge schema is true, well, what's great about this particular option is that then I can do exactly that. I am now saying to myself, no, I want to evolve the schema because it's what we have here is correct, in fact. So let me go do that right now. And sure enough, now I can query the exact same data from the exact same table, the loan by state delta. And in this case, I'm looking at by amount as opposed to by counts. All right. And then we're going to finish this off with time travel and ML flow. Okay, so I want to describe the history of my loan state delta. Remember how I had shown all the files? Well, here's a better view of that stuff, right? So every single change I did, the initial creation, the 6 inserts that we did, the delete, the update, the merge, and the appending that we just did, they're all recorded right here. So now we know what transactions occurred. But what's really cool about this is that because I have those transactions and I also have the original files, if I was to simply go loan by state delta version as of 0, which is the initial what I originally created, I'm literally going back in time, and this is what my table looked like initially. Okay, with where Iowa was null, Washington was 336, not 2700. Oregon was still was 182, not null. California had a different value of 2006. Okay, versus the 9th version of the table, where basically I was able to go ahead and include everything but the inclusion of the amount. And sure enough, here's what the table looks like now. So Iowa's 10, Oregon's null, Washington's 2700, California's 2500. So all of that is actually retained. So you can go back in time and recall what version of the data you had assigned to that transaction. And actually, that's pretty powerful, as you can guess. Okay. Well, why is that powerful from a data science perspective? So here's what I'm doing. I'm just simply downloading some US Census data because I'm building a really boring model. Okay. A really boring model where I'm actually combining the delta data, the loan state data, for each and every single different version of that data by the population of that state. Okay, and so that's what this particular set of queries are for. But now what I'm doing is I'm doing for the data version 0, 6, and 9. 0 is the original version, the real version of the data. 6 is the version of data that got modified, where I went ahead and nullified Iowa and increased Washington to 2700, and then the 9th value of it was basically one where I really messed it up, where I also nullified Oregon, added 10 to Iowa, and also messed around with California for the fun of it. Okay, so what I'm doing here is actually just running a standard. I'm actually running Yellowbrick so I can do some residuals, so I can just visualize it. But I'm actually just simply doing, excuse me, a predict the loan count. That's all I'm doing. So I'm doing a standard linear regression. I'm using the exact same metrics for each and every one. It's basically like if I was to deploy the model. So I'm just going to run that right now. Oh, sorry, I'm going to simply run the code. Okay, and then now I'm actually going to run the code. We're actually going to run the predict loan counts for the 3 different versions: version 0, the original, 6th version, and 9th version. The reason I'm calling this out is that I'm sort of faking this concept of data drift. And as you are running your machine learning models, the data can change over time. Now, maybe it's because you screwed up on the model, or I screwed up the model for that matter, or maybe it's because the data actually did change. But how do you know? So what we're doing here is we're going to actually do a run, which is basically, like I said, we're going to do a linear regression. And what's sort of cool is that this model, okay, this is your standard, you pull it right from Spark linear regression. That's all this is. So the only thing I really did to make this somewhat interesting is that I added these statements with MLflow start run, and I also included the data version, I logged the metric, and I logged the model itself. Okay. I also happen to log the yellow brick residuals view as well, just because it's sort of nice. Okay. So that's it. That's all I've really done. All right. So what happens that if I go ahead and click on the runs folder here, all right, all 3 runs are here. And as you can progress, okay, these are the older versions I did last night, but this is the ones that I did live, as you can tell here. Version 0, we have an RMSE of 65. Okay, not great, but not bad. But as you can tell, using the exact same hyperparameters, again, this is linear regression, so not really that interesting, but still, it gets worse. With version 6, this is the one where I nullified, excuse me, I went ahead and knocked up Washington State. Okay, the RMSE got worse, and now I went ahead and changed California, added data to Iowa that shouldn't have been added, nullified Oregon. It's, as you can tell, it's getting worse, worse, and worse, right? And so let me go ahead and click on MLflow and open up the window here. Okay. And by the way, even though I'm running this all on Databricks, this is actually all open source technologies I'm talking about. I just happen to be showing this on Databricks, but this is all open source stuff. Okay, so if I want to do a comparison, I can just compare those 3 different runs, version 9, 6, and 0, and you can you can tell that basically the RMSE is much better when I go go here, right, with V0 versus V6, V9. You can also visualize it here, right here with RMSE to see the different runs, but what I also like about when I'm working with MLflow is that I actually, for example, I'm looking at this one, version 9, right? So I can tell the RMSE is horrible, right? But I've also went ahead and, like I said, I went ahead and did yellow brick, and I looked at the residuals, and right away I can tell. Okay, by the way, train basically means the V0 data, and test means the V9 data. Like the training data basically is 0.97, so the R squared is actually not bad, but the R squared for my V9 data is really horrible, right? And so it's really clearly indicating the drift here, like the changes to the data. Now, of course, this is known because we manually manipulate the data. But the context here is that as time progresses over time, you have that ability to go ahead and, with Delta Lake, not only be able to reliably look at your data and trust your data, but you actually have data versioning, so you can figure out what the heck's going on, and if things have changed or progressed, it's okay. You can go back and verify, yes, my V0 model actually looked good. And so for that matter, you can even redeploy the model. So we have the ML model right here. It tells you exactly which version that you were using, what Python version, what Spark ML, the conda that goes with it. So these are the dependencies. So MLflow, this version of PySpark, this version of Python, and for that matter, all the metadata and the stages for your ML model are now stored directly in MLflow. So I can go back and redeploy it, or go back and change it. So because there's always invariably the issue that maybe the data that came in, actually there were problems, but then later on it got cleaned up and fixed, so you can go back and use this model. Okay, so as you can tell, there's a lot of power by combining these 2 open source technologies together to help you go ahead and get yourself data ready for data science. Okay, so I'm going to finish up my presentation here, and then I'll still leave a little bit of time for questions. So, hey, how do I use Delta Lake? Okay, so to use it, obviously, we're going to give you this notebook, and you're going to be able to download stuff. That's great. But if you want to run this yourself and you don't directly write from terminal or from a Jupyter notebook, that's fine. Add the Spark package. It goes -- packages, io.delta, delta core. I'm using Scala 2.12. The current latest version is Delta Lake 0.5.0. So there you go. And then I'll keep on updating the slide deck when we keep on updating the Delta jars, which we're doing at a roughly about the 6 to 8 week pace. Okay. You can also, of course, use Maven, which is then right there. Same idea. Your artifact ID is Delta Core, which Scala version, the version, or the current version as of this recording is 0.5. When you write, instead of using Parquet, in other words, dataframe.write.format Parquet, just simply change it to dataframe.write.format Delta. And that's it. Now, just like that, you're using Delta Lake, okay? And we already talked about the update merges. We already talked about the time travel. And yes, because I have that time travel capability for 10, a bunch of those steps, 6, 7, 8, 9 were wrong. I can now roll back. This is an example of it, but basically I can go roll back to the 6th version. And so now from this point onwards, I'm back to version 6 of the data, or sorry, version 0 of the data for that matter, the data that I actually can trust, okay? And so this is a small but fundamental component of that data science lifecycle that allows you to go ahead and have reliable data, that by basically adding Delta Lake and MLflow, that you can ensure that no matter what tools you're using to do your analyses, no matter what tools you're using to do your processing, you're actually going to have a reliable data lake, and you can track both the data version itself and the model versions that you're working with. Okay, so if you want to build your own Delta Lake, please go to htssdelta.io. And Delta Lake has actually gotten more and more popular over time. We have various connectors. We're currently working on Hive. Presto's already out. We have connectors for Snowflake, Athena, Redshift, and Hive should become publicly very soon. There are lots of providers and partners, whether it's Tableau, Informatica, Qlik, Privacera, Tundi, Talend, Wendisco, StreamSets, and Google Dataproc recently announced that they are supporting Delta Lake as well, which is pretty cool, right? And as you can tell, there's a ton of users, so I'm not going to go through them all, but there's a ton of users of Delta Lake. We constantly update the Delta.io page for all that. If you want the notebook from today's webinar or Tech Talk here, try it out in Databricks Community Edition, and you can download it from this link. We're going to send you this email out with all this information anyways, but which includes these slides, by the way. But yeah, it's right there for you to download and try out. Did want to call a couple things before I answer questions. Hey, you got more questions you want to dive into deeper? Why don't you join us at Spark and AI Summit? Okay, Spark and AI Summit, June 22nd to 25th in San Francisco. We actually 2 training days now, just because of the popularity of them. It's organized by Databricks, but listen to the open source technology. So come on down. It's in San Francisco. Use the code Denny. My name Denny SAI 020. Okay. That's the code. You get 20% off. So go ahead and give that a shot. Would love to see you down there. Love to answer your questions both online and also face to face. Okay. And also, if you have questions, come to delta.io or mlflow.org. We actually have a ton of questions where we can actually. We're very active on our Slack channels. We're very active on the distribution list. So definitely go ahead and join us there. Okay. So saying that, I'm going to leave you at this. I'm going to leave a few minutes for questions, and we'll go from there, okay? Sorry, I am trying to open the QA, but it's not opening. All right, let's just open the chat. Okay. So, okay, I'm going to go through looking at the questions here. So I apologize. I'm just trying to scroll through them right now. There is a question, oh, by the way, as a small joke here, when I did say morning, everyone, and it's a good morning for San Francisco, that's from Karen. I'm actually Seattle based, so just as a quick call out. There's a question about, is there a difference between Databricks Delta, as in the Databricks version, versus the open source one? There's no difference between the APIs by version 1.0. Most of the API differences are all resolved now, but I do want to call out that, since we're a pre 1.0 project, we're still trying to make sure that all of the functionality that exists in Databricks Delta from a reliability perspective are included in the open source version. Okay. Oh, by the way, if you're asking questions, please don't use the Q&A panel. Please put it onto the chat panel. For some reason, my Q&A panel is not opening right now. And so by version 1.0, if not earlier, we'll actually ensure that every single feature that exists in Databricks Delta is also available in open source Delta Lake. Now, what is the difference then? The difference right now primarily is, for example, some of the update delete statements that you saw, those are not going to be ready. You can run updates and you can run deletes, but you can only run them from the Python and Scala APIs in the open source one. We're actually waiting for Spark 3.0 to release with Data Source v2 that'll allow us to actually make some of the changes that allow us to go ahead and put the SQL statements in as well. So that way you can use Spark SQL for deletes and updates, like I'd shown you on the screen here, as opposed to using the API. But if you want to use the API, obviously you can use the API right now to do deletes, okay, and updates and merges. And so the main difference post 1.0 is that all of the APIs will stay exactly the same. It's just that Databricks itself is a managed service. So because we're a managed service, we're going to go ahead and run Delta Lake for you. We're going to manage it. We're going to do performance enhancements, things of that nature. But it is a open source project. It's part of the Linux Foundation. So if you are going to put in PRs, yeah, we'll probably take them, right? Because it is an open source project. So we want to make that very clear. But right now, at least, that's the primary set of differences, okay? So there's a question, can I change the Delta Store to Blob, Lake Store, DB? Not to DB, at least certainly not yet, but you can certainly make the changes for Delta Lake to be pointing to whatever a file store that you want. So in other words, you want to run this on the Hadoop file system, by all means. If you want to run this on the Azure Data Lake Gen 2 or S3 or Google Cloud Storage, these are fine. There's actually nothing stopping you from doing that. Because if you recall, in the end, the primary thing we do is we add an additional folder _delta_log where we put the transaction log into it. That's the primary difference that we've made, right? Outside of that, it's still technically the same Parquet files that you would see in a Parquet table on that file system, right? So we're still doing the same thing. There are certainly some optimizations done underneath the covers, but for all intents and purposes, it's still Parquet files. The most notable change is that you, when you're trying to look at the data, there's a lot more data in there, right? So for example, when I do a delete, technically I'm not doing a delete, right? Technically I'm building up a tombstone, because what I've done is I've created a new version of the data that doesn't contain the data that I deleted. This is the reason why I can go back and use time travel to basically build up the different versions, right? I can go back to version 0 and have the version of the data that says Iowa was null and Washington is 336, because the data still actually exists, right? It's still there. It's just that basically because the transaction log allows me to keep track of that. All right. So that's the main difference. So if you try to, for sake of argument, have multiple transactions on your Delta Lake table, but then you try to just read the Parquet logs without actually reading the Delta log, there could be multiple versions of this data. So then presumably you could see duplicates or triplicates or so forth, because you're actually seeing like the previous versions of the data as well. So because it's an open source project, actually, we recently released a blog, Delta Lake 0.5.0, where we actually talked about manifests. And this is where Presto and Athena can actually go ahead and take a look at the Delta Lake data. They can look at the Parquet data, because what you do is you generate a manifest file. The manifest file basically simply contains, here are all the files that you should be looking at for the most current version of data. That's it. And so, like for sake of argument, there are 20 files inside there, but if you want to look at the most current version, you only need to look at the 6. So the manifest basically contains the file names of those 6 files. And then Presto and Athena can read that manifest, which then invariably tells them to go look at those 6 files. And from there, you're pretty much good to go. Okay. So hopefully that answers that question. So actually, in this case, I apologize, but I think our time is up now. So I will go ahead and probably end this session now. By the same token, if you do have questions, I highly would advise you to join us at delta.io or join us at mlflow.org. And as well, we will be sending an email out. Well, actually, not so much an email out, but we'll be sending out